So what I wanted to talk about here specifically are two of the technologies that we've brought up lately that are actually pretty exciting. I suspect all of you, even if you're not computer scientists, are going to love these things. So one of them is going to be Big Table, and the other one's going to be CQRS. So has anybody here heard of CQRS, like mentioned casually anywhere? Maybe not. That's okay. You guys get excited because you're going to hear about it today then. So anyways, one of the things I wanted to talk about is for any of you that went to school, you guys have definitely seen this diagram. They call it the 7-layer OSI model. And this is the gold standard for how you're going to implement a network. And so one of the things for everybody here in the audience that this model promises for you is that all the programs on your computer that you're going to use, you don't have to care whether you're using a cable modem or whether you're buying your internet from SaskTel or whether you're using your cell phone, because that's irrelevant to the application you're using. And that's what they talk about here, is having a layer model. So essentially, you can substitute layers at the bottom of this thing without affecting the layers at the top. And essentially, the promise of this model, which I mean, everybody who's in computer science probably realizes that this is not actually the model that we use for networks, but that's okay. What we're talking about here is that you can implement stuff at a higher level and change out these lower layers because there's a standard interface. So what this actually means is that in terms of your internet provider, they have a standard in terms of what they provide you in terms of like, this is internet, this is, it's an IP layer. And so what's gonna happen is it doesn't really matter whether they use ATM networks or IP networks underneath. It means that you can substitute those out and hey, it's kind of exciting. And so this is something that's happened in hardware for a long time, and the object-oriented guys will say this has always been a big deal, and we've definitely always done it. But you guys have also probably heard a new model that people talk about, which is microservices. Whoa. And essentially, microservices are kind of the big new trend, and this is one of the things where we're saying, hey, wouldn't it be great if when you called some sort of an API, we could change out the implementation without you actually breaking all the clients? And everybody in the computer science audience is like, awesome, it's object-oriented programming 101, except we've got a new name and it's a big buzzword, and everybody's talking about it in 2016. But the interesting part about this is that this picture here comes from Uber. And so the idea from Uber is that they've got a couple of different microservices. And so one of them is related to passengers, one of them is related to drivers, and one of them is related to trips. And the idea is that you're probably only needing to deal with one of these contexts at a time. You're probably not interested in talking about when you're talking about drivers, you just want to find a driver to take you on a trip, but you haven't actually planned one yet. And then in terms of you're looking up your trips, you're probably not looking at who the passengers were and a whole bunch of details about them. So they kind of segregate this out, and the idea is that, great, you've got a couple of different data sources, and we can actually change those out without affecting the other services. So this is pretty exciting, but one of the things that this picture always shows you is you've got an API here, and then you've got one data store. And so one of the questions you have to ask here is, why is it that I have to actually tell it what I'm interested in? And one of the examples I think would be interesting is, like an analogy to something everybody's looked at is, can you imagine if when you phone 911, one of the important questions they asked you is, all right, we've got fire, we got police, and we've got an ambulance. Like, which one are you looking for? And if you're going to say, like, I've got a whole bunch of people in a burning house, and their choice was, well, you want us to put the fire out, or do you want us to help the people? So, like, it's a pretty old concept that you can imagine that a service like that you would call like 911 would have like, hey, one interface, or let's call it an API, that you would call in and maybe tell them what you wanted, which is, I have a burning house, I need help. And they would choose to send whatever they needed. And they might ask you some clarifying questions. But this is essentially what these microservices can offer. And the idea on this picture is that how they actually implement the solution, how they're going to deliver you the result, you really don't care about. Because when I phone 911, because I've got a fire, there's injured people, and there happens to be a drug war happening on the lawn, I don't want to have to understand how best to handle that situation. Much like when you call an API and ask for something like Brent was talking about earlier today, like, I want all the reviews aggregated across 15 things and I'd like to return it. You don't want to have to know that, oh yeah, make sure you put that in Elasticsearch because I know all about pipeline aggregations. You'd like that to be hidden from you. In terms of, you like your microservice to hide some of that stuff. And so that's what we're talking about actually doing a bit more of, and I wanted to talk a little bit about one of the other things that comes up here quite a bit. And so for us, one of the things that microservice architecture talks about is you've got one data store behind a microservice, but the question you ask is, Why do you only have to have one data source? Because if you're truly abstracting the details behind and like what's underneath, why not be more like 911 or something and have multiple options for how I actually fulfill the request I'm going to give you? So in terms of our case, or maybe your case, when you go to a restaurant, why would you have to choose between soup or salad? Maybe you could have both. The interesting thing here is that for us, we're going to choose to store this data in multiple formats because depending on what you need to do, we might actually choose to source it from one or multiple data sources to actually accomplish that. And so in the case of what Brent was talking about, maybe you want to have some details of your service that offer full text search, but maybe other ones are going to do a lot of relational data. And I mean, Elasticsearch doesn't work for that. And so on a traditional data model where you have one data store, you're forced to make the choice of, what do I actually want to be good at? Do I want to be good at maybe searches, or do I want to be good at aggregations, or do I want to be good at key value lookups? And I think at one point we basically said, well, I don't want to have to choose. I'd actually like to go ahead and be good at all of these things. So one of the things that everybody here that went to computer science as well is going to have heard of is, as soon as you start dealing with replication between data sources, it's the classic adage is, more replication, more problems. How many people are here have heard of the CAP theorem? So CAP theorem, the way that most people state this, which is incorrect, and I put that up here, is that you get consistency, availability, and partition tolerance, and you only get to pick two. But that's actually not the way the CAP theorem works. What CAP theorem is actually talking about is, in the event of a partition, do you choose consistency or availability? So for everybody that I just lost there, don't worry, I'm planning on explaining exactly what that means. So what this means is, you can imagine that replication means keeping two copies of your data. So as an example, let's say that I had on a sheet of paper the inventory from my store and everything that I stocked in my store. And you know what? I pick up the phone and I use this sheet of paper to answer what's in stock in my store. But at some point, maybe I can't handle all the phone calls. So I say, hey, Nakia, I need your help. And so what I say is, Nakia, I've made a copy of all the items that are in the store. I want you to also deal with the phone, and you can tell people, hey, what do we have in stock? And so the idea of what a partition means is, let's say Nakia and I are in different rooms and we actually can't talk to each other. The question comes up when someone actually says, you know what, I want to purchase an item from your store. What has to happen is Nakia and I have to talk and say, okay, what we have in stock is actually different, Nakia, because I just sold one of these hammers. And so we have to have some sort of communication, otherwise we could actually oversell. We could sell more than what the store actually has in stock. And so the question comes up is, how do we deal with a scenario where Nakia and I actually can't talk to each other? And so in a consistent choice, aka if you decide to store data in a consistent approach, it says that if I can't talk to Nakia, I will deny your request to purchase hammers. I'll be like, I'm sorry, I can't talk to Nakia. You can't actually buy anything until I can actually reach her. And this is how traditional databases work, like relational databases, in terms of if you can't actually, and I mean some of the terms if you go into details like quorum and things like that, if you can't establish a quorum, aka an agreement that, hey, this is actually the truth, you'll actually reject those opportunities to make writes or reads. And so the other option is maybe Nakia and I make an agreement and we say, you know what? If I can't talk to you, you just go ahead and sell those hammers anyways. And when we figure it out later, when we can actually talk, we're going to have to figure stuff out. And they call that reconciliation. And so there's different databases that essentially choose between a consistent approach versus an available approach. And so the answer is that at some point, if you can't talk to all the nodes, you have to decide, are you going to go ahead and service requests despite being able to promise that you don't know the whole truth? Or are you going to go ahead and say, like, I can't service stuff until I know the whole truth? And so part of that thing also comes up is that there's another theorem that came up in about 2010 that's called the, and again, this is a terrible pronunciation, but I guess that as the guy that came up with the theorem, you can name it whatever you want. It's called the Pass-Elk theorem. And so the idea of what this thing says is that the first theorem, which is CAP, says, hey, we're going to talk about a database only in the case when there's a partition. But I mean, if you're running a real data store and it's actually connected to other guys, hopefully the average case isn't when they're disconnected. And so this says that maybe how a database operates when there is no partition is also relevant. And in that case, in terms of the analogy that I had for Nakia and I and us running a store, is we can choose between latency and consistency. And so what this means is every time I go ahead and take a sale, let's say, I would have to say, hey, Nakia, is it cool if I actually sell this hammer? In that case, you can imagine that latency goes up because I have to wait until Nakia tells me, yeah, it's cool, go ahead and sell that hammer. Or I could choose, yeah, you know what, I don't even care what Nakia says. She'll get it figured out later. And I can say, yeah, I'll take that order right now and then update Nakia afterwards. Now, again, you can run into conflicts in that case. So these are things that databases end up having to choose between. And so this is something that's obviously relevant to us because we're talking about doing replication. And so one of the things that we did is we got really excited about replication and maybe didn't appreciate some of the finer details of exactly what that entails. And so we actually started implementing this because we had all of our data in a place called Data Store, which is a technology from Google. And this is where we stored most of our stuff. And this is optimized database if you just know exactly what it's called. And so this is a key value get is essentially what this optimizes for. And so that means if you were to come into a store and you were to say, I'm exactly interested in, let's say the Stanley, let's say it's a, I don't know, let's say it's a 12-pound dead blow hammer. That's what you're interested in. That's what Data Store specializes in. It's very quick to get exactly that one. But if you came in and said, you know, I want a hammer and I don't really know exactly which one, it's actually not optimized for that kind of case. And that's where Brent's talk about Elasticsearch came up because we said, you know, we really like people to not have to know exactly which one they wanted. It would be nice if we could maybe do some searching and figure some stuff out. So what we ended up doing was we used post-put hooks, or for those of you with database experience, essentially this would be like an RDBMS trigger to cause that replication. But unfortunately, one of the things that we lose there is because we force the clients essentially to do the work. You know, if you didn't implement your replication logic correctly, you could have missed out on actually, you know, properly doing it in a transaction. And so one of the important parts of a data store is that, I mean, you'd like it to be what they call durable, which means if I actually write something to a database, you'd like to make sure that it actually happened. And so that's one of the things that actually was not 100% guaranteed. And in a system when you're doing like millions of writes and reads in a day, anything less than 100% on durability is kind of a problem. And so, you know, it would have been probably 6 months ago that we sat down and talked and said, you know, as we're getting this number of things in our Elasticsearch, which I think Brent was saying is 700 million, it's starting to be a big deal that we don't have a 100% guarantee that the stuff is actually in there. And so we decided we probably needed to make a little change. And so, there we go. We decided to make a little bit of a change. And so this is actually not a picture of Big Table. It's a picture of a Big Table. But this is a technology that we decided to use. And so unlike Data Store, which actually in terms of our CAP theorem makes a choice of availability over consistency, Big Table actually makes a choice of consistency. So in a lot of ways, it's more like a traditional database, but it's just a key value store. And so it actually offers very similar capabilities to Data Store, but it offers that consistency. And then what we did is we combined Big Table with a tool called PubSub. And so this maybe seems like a small detail, but this is probably the crux of exactly what we were trying to do here. Because in terms of a replication story, what you want to be able to promise is that if you write it to the primary, and the primary database says, yeah, I got that, you know that eventually all of the read replicas, all the copies. So in the case of this, the idea is that if you turn out, and I mean, Nakia and I run in our hardware store and you purchase a hammer from me, eventually at some point later, I'm gonna tell Nakia that I sold it or that we acquired more stock. And the idea is that, you know, we're not just running totally separated. At some point we get synchronized. And so that's what the promise we're offering here. So it means that in terms of what PubSub guarantees for us is that as soon as we actually send a PubSub, it guarantees that anybody that receives it will receive it at least once. They could receive it 5 times, they could receive it 10 times. Highly likely they receive it once, but they promise that they won't receive it 0 times. And so what this means is a reliable way for me to communicate with, let's say, Nakia in our case, or if I had 10 other people, PubSub actually allows me to say that I promise all 10 of them will get it at least 1 time. And so it makes it so that we can actually have some processes to guarantee that when we write stuff into our primary data source, that all the replicas eventually are going to catch up. And so there's a bit of work to actually make that happen. And that was where, you know, we had a couple of guys, Dustin and Braden, doing quite a bit of work on this stuff. But we actually went through and tested. And this stuff actually happens in the event of what we called partitions. And in, I mean, all honesty, I mean, CAP refers to it as a partition and it sounds kind of nonchalant. But that could be like, you know, a data center burns down. That could be hard drives die. That could be network latency. There's lots of opportunity, like things that can happen. And actually, even a few weeks ago, we got a big warning from Google. There was a giant hurricane coming to one of their data centers, and they said, you're probably going to experience a partition. This is a tornado ripping a data center into the air, and it's called a partition. But anyways, it was kind of funny. It didn't actually happen. Luckily, it missed, I guess, at least for those people that weren't ready for it to happen. But so that was the solution we ended up choosing here, is that so we have a primary and we have a pub sub. And the biggest part of this is that the change that we made from the previous one is that instead of having the clients deal with the replication themselves, we actually manage that part for them. So we give that guarantee that at least once we're going to make sure to send this message. And so this is actually, I guess, the meat and potatoes of what we wanted to do, was to promise both some sort of consistency model, which in our case is eventually consistent. It's a highly consistent primary with an eventually consistent secondaries, but the durability of those secondaries is also guaranteed. So that means that we're not going to have cases where things don't get replicated and we have to deal with it. And specific things that are covered and tested for is like node failures, service outages, even application bugs. These kind of things, it's very important that we actually catch them all. So this is kind of the stuff that we implemented here, and by using Big Table and Pub Sub, we've actually been able to build this stuff up, and we actually rolled this out this week as doing some of the Elasticsearch replication. So the interesting part is, to the end user, it actually looks like nothing's different, which I guess in some ways is less rewarding. In other ways, I guess that's exactly what you want, is to be able to switch out the whole back end and have actually nobody notice that it's any different. It's just really hard to sometimes sell the higher ups that you actually did anything. So anyways, that's kind of what we were doing there. And I guess, like, to explain the secondary indexes, I feel these cats were a really good way to do it. Is they kind of, you'll notice what's happening is they're kind of all doing the same thing, but there's a little bit of lag between them. That's an easy way to think about exactly what our data sources look like. You've got one guy that's definitely getting the cues, and everybody else is kind of following along, and eventually they catch up. These cats are actually very well trained to keep up. It's probably really tough. But in terms of our system, what we're going to be using this stuff for is actually implementing it with a primary and Big Table, which is just key value, but then the ability to replicate that for Elasticsearch, ability to replicate that for something like a MySQL, and even a Redis, which is a key.get, which is similar, except for that it's even faster than Big Table. So some of these things are possible, and it makes a big deal for us. And I guess the one thing that I wanted to mention about this system that's kind of another buzzword that you'll hear about is it works on something called a declarative state. And so the way we do this is in our Big Table, when we write data to it, we write down that, hey, we haven't done any of the replication. And then once we receive a successful response from PubSub, we actually update those records and mark that, yeah, we did receive a successful replication. And so for us, what that means, they call it declarative state, because essentially Big Table contains this record and it says what replication has been successful. And essentially our system continuously iterates over that value and says, hey, is it successful yet? If not, let's try again. Hey, is it successful yet? Let's try again. And it does that forever. So if the network goes out and we're unable to replicate, at some point when the network comes back, because we're hoping at some point it comes back, when it does come back, that check will actually force that replication to happen. And so that's where the eventual consistency, and in terms of our CAP theorem for that stuff, we actually choose availability, which means that those read replicas could be out of date if there's a network partition or something, but eventually it's going to get there. So that's kind of what we talked about there, and that's probably the bulk of it. So in terms of, I didn't actually call this by its name, which some people like. CQRS is the buzzword that you're going to hear about this, and what that actually means is they call it command query responsibility segregation, and this is a keyword thing for you if you're wondering what that means. Commands are basically writes, queries are basically reads, and they're saying that they should be separate. So in our system, our commands go to Big Table, our queries go to whatever places we decide to replicate to. And the interesting part of that is it allows us to choose a data system that actually optimizes for reads and writes separately. Because you'll notice when Brent was talking about Elasticsearch, you get a choice of how do you want to configure it. Do you want to optimize for reads, or do you want to optimize for writes? And what we kind of said is we don't like that. We like to optimize for both.